Good morning. Today we are going to discuss selectivity, conversion, and yield. We're still going to solve problems from Himmelblau. Let me share you the PowerPoint. Okay, so first we're going to tackle some problem that introduce the concept of yield. So basically yield is uh, it can be expressed as grams of product per grams of raw material, or moles of product over moles of raw material. So it depends on the problem what is being asked. So let's try to solve example 9.6. Yields in the reaction of glucose to produce ethanol. Yeasts are living organisms that consume sugars and produce a variety of products. For example, yeasts are used to convert malt to beer and corn to ethanol. The growth of S. cerevisiae, a specific type of yeast on glucose, a sugar, under anaerobic condition in the absence of oxygen, proceed by the following overall reaction to produce biomass, glycerol, and ethanol. So glucose, C6H12O6, plus 0.118 ammonia, that's NH3, will produce 0.59 mole of CH1.74 NO2 0.45. That's your biomass empirical formula. Plus 0.43 C3H8O3, that's your glycerol. 1.54 moles of CO2 and 1.3 moles of C2H5OH, or this is your ethanol, and 0.03 mole of water. Calculate the theoretical yield of biomass in grams biomass per grams glucose, and also calculate the yield of ethanol in grams ethanol per grams glucose. So first, let's try to calculate grams of biomass per grams of glucose. So basically, ang gagawin lang natin, we're going to use 1 gram of glucose as our basis. So we'll start with 1 gram of glucose, and then we're going to convert the weight or the grams of glucose to mole of glucose, and then we're going to use the stoichiometric constant in the reaction to calculate the number of pounds, moles of biomass, and then multiply the result with the molar mass of biomass to obtain or to calculate the grams of biomass per grams of glucose. Let's try to do that. So let's start with 1 gram of glucose. So the molar mass of glucose is 180. So we simply divide this by 100. For every 180 grams of glucose, this is equivalent to 1 mole of glucose. So now that we have the number of moles of glucose, we're going to use the given reaction. So for every 1 mole of glucose, you'll be able to produce 0.59 mole of biomass. So times 0.59 mole of biomass, just for every 1 mole of glucose. And then finally, multiply this by the molar mass of biomass. So if we're going to calculate the molar mass of biomass, you'll be able to get 23.74. Okay? So 23.74 grams of biomass for every mole of biomass. Okay, so all you need to do now is try to calculate the answer for this equation. So 1 divided by 180 times 0.59 times 23.74. 0.0778. So this is grams of glucose per, also grams of biomass per grams of glucose. Okay, so let's try to find out the second value of yield. This time in terms of grams of ethanol per grams of glucose. So likewise, we're going to start with 1 gram of glucose. And then again, convert this to mole of glucose. So for every 1 mole of glucose, we have 180 grams of glucose. Uh, for every 1 mole of glucose, you'll be able to produce 1.3 mole of ethanol, so times 1.3. And then finally multiply this by the molar mass of ethanol. Ethanol is 46 grams per mole of ethanol. Okay, so just going to use the calculator. Okay, so it's about 0.332. This is grams of ethanol per grams of glucose. So it's very similar to your analytical chemistry. You just need to convert the weight into moles and then use the reaction to find the number of moles of the product, and then use the molar mass to convert that to mass. Okay. Next, let's define selectivity. So selectivity, or S, is generally defined as the number of moles of the desired product divided by the number of moles of the undesired product. ND over NU. Okay. So Usually, in a chemical reaction, we have two parallel reaction that is going on at the same time. So one is the major reaction or the reaction that we wanted, and then another is the undesired reaction. So usually the wanted reaction produce the desired product, and the other reaction produce the undesired product. So most of the time we wanted to optimize the condition so that the condition will produce more of the desired product. So that's the practical use of selectivity. Let's try to solve some problem regarding selectivity. Okay. So this is example 9.7, selectivity in production of nanotubes. A carbon nanotube may consist of a single wall tube or a number of concentric tubes. A single wall tube may be produced as an aligned structure or bundles of groups packed together in an orderly manner. The structure of the nanotubes influences its properties such as conductance, some kinds of conductors, and some semiconductors. In nanotechnology, numerous methods, arc discharge, laser vaporization, chemical vapor deposition, and so on, exist to produce nanotubes. For example, large amount of single-wall carbon nanotubes can be produced by the catalytic decomposition of ethane over cobalt and iron catalysts supported on silica. So we have two reactions. The first one is we have ethane, C2H6, producing 2C. 2C is your nanotube, plus 3 moles of hydrogen gas. That's the first reaction. The second reaction or the side reaction produces ethylene or ethene, C2H4, plus a mole of hydrogen gas. If you collect 3 gram moles of hydrogen gas and 0.5 gram mole of C2H4, what is the selectivity of C relative to C2H4? So as you can see from the given, C is the desired product and then C2H4 is the undesired product. So it's just S. Selectivity or S is number of moles of the desired product divided by number of moles of the undesired product. So basically, this is number of moles of C all over the number of moles of C2H4, undesired product. So as you can see from the problem, we have 3 gram moles of hydrogen. So since hydrogen is coming both from the first reaction and from the second reaction, not all of this hydrogen is coming from the production of nanotubes or carbon. So as you can see, we have 0.5 mole of C2H4. So basically, you need, for every 0.5 gram moles of C2H4, you're going to produce 0.5 gram moles of hydrogen. So of this 3 gram moles of hydrogen, zero point 0.5 gram mole of this hydrogen is coming from the production of C2H4. So only 2.5 gram moles of hydrogen is associated with the production of carbon. Okay? So 3 mole H2 minus 0.5 mole H2 will give you 2.5 mole H2. So with that 2.5 mole H2, so you just use the stoichiometric ratio in reaction A. For every 3 mole of H2, you're going to produce 2 mole of carbon. So multiply that, For every 2 mole of carbon, you're going to produce 3 mole of H2. And then you just divide this by the number of moles of C2H4, which is 0.5. Okay, so just use your calculator to calculate selectivity. It would be 2.5 times 2 divided by 3, 0.5. 3.32. So selectivity is equal to 3.32. Okay. Okay, next drawing. Next slide.
Nagbababaan ka sa table. Ba't kayo dito sa table?
Okay, so this is the last problem. Calculation of Barr's term pertaining to reaction. So Seminov, Some Problems in Chemical Kinetics and Reactivity, Princeton University Press, 1959, pages 39 to 40, describes some of the chemistry of allyl chloride. The two reactions of interest for this example are chlorine gas plus C3H6 gas, that is propylene. You're going to produce C3H5Cl. This is the allyl chloride. This is used as raw material for several pharmaceutical products, plus hydrochloric acid, plus hydrogen chloride gas. And then the unwanted reaction is chlorine gas plus propylene, plus propene or propylene, producing propylene chloride. Okay. The species recovered after the reaction takes place for some time are listed in table E 9.8. So as you can see, in the end of the reaction, you have 141 moles of chlorine, 651 moles of propylene, 4.6 mole of allyl chloride, 24.5 mole of propylene chloride, and 4.6 mole of HCl. So based on the product distribution, assuming that no allyl chlorides were present in the feed, calculate the following. The letter A, how much Cl2 and C3H6 were fed to the reactor in gram mole? So basically, for letter A, you're just going to add the remaining chlorine gas. The number of moles of chlorine gas is still present, and the number of moles of C3H6Cl2, that is your propylene chloride, plus the number of moles of allyl chloride. Or you can have the allyl chloride divided by 2 plus number of moles of HCl divided by 2. That is more exact. Okay, so let's for letter A, let's try to calculate the number of moles of chlorine initially. So letter A, moles of chlorine. So we can take a look at the table. We have 141. Okay. And then 24.5. And then we have 4.6 for HCl. So we need to divide this by 2 because HCl contains only 1 Cl. And another 4.6 divided by 2 for allyl chloride, since allyl chloride contains only 1 chlorine atom. No? So we're going to get the sum of these three. we're supposed to get 170.1. So initial number of chlorine is 170.1. Huh? Okay, so likewise, so we're going to calculate the number of moles of initial number of moles of propylene, C3H6. We just uh, add the number of moles of propylene or propene still present, 651 moles, plus the number of moles of propylene chloride, 24.5, plus the number of moles of allyl chloride, 4.6. So all in all,
Ilagay ko pa yung chicken doon. Bumili ko lang sa tindahan.
we have 680.1. Okay. So the next question is, what was the limiting reactant? If you're going to examine the two reactions, reaction A and reaction B, both the reaction has a stoichiometric ratio in the reactant of 1:1. No? So 1Cl2 for every C3H6 to produce C3H5Cl, and 1Cl2 for every C3H6 to produce C3H6Cl2. So you can conclude that the reactants which has lesser number of moles will be the limiting reactant. So in this particular case, Cl2 initially has lower number of moles. So therefore, Cl2 is the limiting reactant. So since Cl2 is the limiting reactant, therefore, the excess reactant is propylene, C3H6. Okay. Let's go to letter D. What was the fraction conversion of C3H6 to C3H5Cl? So, as you can see, C3H6 is both converted to C3H5Cl and C3H6Cl2. So what we're going to do with letter D is we're going to get the number of moles of C3H6, and then we're going to get the number of moles of C3H5Cl, and then divide this with the initial total number of moles of C3H6, which is 680.1. Okay? So letter D. Okay? Just try to find the number of moles of C3H5Cl. Then divide this with the total number of moles of C3H6. So from the table, C3H5Cl is 4.6. It's 4.6. And then if you still remember, C3H6, initial value of C3H6 is 680.1. So just use your calculator to get this ratio. (6.76 times 10 to the minus 3). Okay, so that's the fraction of propylene converted to C3H5Cl. Okay, let's try letter E. What was the selectivity of C3H5Cl relative to C3H6Cl2? So basically, since it seems to be that C3H5Cl is the desired product, and then C3H6Cl2 is the undesired product. So you just simply divide the number of moles of C3H5Cl with the number of moles of C3H6Cl2. So in our table, C3H5Cl is 4.6 and C3H6Cl2 is 24.5. So that's how we're going to solve letter E. Okay, so selectivity, number of moles of desired product divided by number of moles of undesired product. So desired product is C3H5Cl. Undesired is C3H6Cl2. So just this is 4.6 and then this is 24.5. So 0.19. Okay. And then letter F. What was the yield of C3H5Cl expressed in grams of C3H5Cl to the grams of C3H6 fed to the reactor? So basically, yung mole per mole ratio, i-multiply nyo lang ng corresponding molar mass. No? Yung letter F. Letter F. This is yield. You are asked to calculate the grams of C3H5Cl per gram of C3H6. So C3H5Cl is, we have 4.6 mole. So just multiply this with the molar mass of C3H5Cl, which is 76.45. And then C3H6, we have 680.1 moles. We just multiply this. C3H6 is, ayun pala. Ito pala yung mga molar masses. Ano? So, C3H5 is 76.53. You can use that 76.53. And then C3H6 is 42.08. So, letter F. .0123. Correct, 0.012 nasa libro. Okay. So letter G, what was the extent of the reaction of the first and second reactions? No. So if you still remember, the extent of the reaction E is equals to N sub I minus N sub IO divided by B sub I. So for the first reaction, we're going to use the stoichiometric coefficient for C3H5Cl. Or we're going to use the values for C3H5Cl. So initially, C3H5Cl is not present or zero. And then after the reaction, you have 4.6 moles of, let's clear this up. You still remember letter G? Letter G. The formula for the extent of the reaction is N sub I minus N sub IO divided by B sub I. So in the case of reaction A, we're going to use C3H5Cl. It will be N C3H5Cl minus initial N C3H5Cl initial divided by V sub I. So the stoichiometric is 1. So this is a product, so positive 1. V sub I na? BC3H5Cl. So to substitute the values, the final ano is 4.6 minus 0 divided by 1. So it will be positive 4.6. Okay? Still remember the equation for extent of the reaction? And then for reaction 2, still on letter G, reaction B. So the same equation for extent, Ni minus NiO divided by Bi. For reaction B, it would be N C3H6Cl2 minus N C3H6Cl2 initial divided by B sub I. So this is 24.5 minus 0. Initially, there's no C3H6Cl2 divided by 1. So extent of the reaction is 24.5. Yung letter H is very specific. We'll leave that. Okay. Okay. So these are sample problems regarding yield and selectivity. So see you again in the next video tutorial.